this guy right here, empirical formula notes. That one? We see it? Okay, empirical formula notes. We're just going to jump in with a practice one here. And I don't even want to start with the first one. I want to start down here with number 3. Okay, so I want to start with this one that says 140 gram sample. Do we see where I'm at here? Can you find that on your sheet? Okay, so let's go ahead and try it here. Do you have your list of steps out in front of you? And we have our periodic table and our calculators out? Okay. This says 140 gram sample of an unknown compound contains 2.24 grams hydrogen, 31.08 grams nitrogen, and 106.6 grams of oxygen. Okay, what is the empirical formula of the unknown compound? So we want to figure out what is our unknown compound. Now, is our information given to us in percents or in grams? It's given to us in grams, so I don't need to make any switch, but I am going to go ahead and start. If I don't have to make the switch, what's my next step? Converting them to what? Moles. Okay, so here's what I do. I'm going to start 2.24 grams of hydrogen, and I know I'm going to convert that to moles. And so I kind of just make myself a little workspace here. Grams of nitrogen, and I'm going to convert to moles, and then grams of oxygen. And I know I'm going to convert to moles, right? I'm going to do a little T-chart for each of these to convert them to moles. Okay, so I kind of list them out. And then I can go in and back in and fill in my numbers for each conversion. Okay, if I want to get rid of grams of hydrogen and go to moles of hydrogen, right? I'm just going to put in moles gets the 1. And what goes here with grams? Do you remember these mole conversions?
Oh, it's just their mass.
Their mass, that's right. So hydrogen's molar mass is just 1. Okay? And so if I do the math on that, that comes out to be 2.24 moles of hydrogen, right? I didn't have to do much math with it. Okay, moving on to nitrogen. We're going to get rid of grams of nitrogen, right? It comes down diagonally. So grams of nitrogen to moles of nitrogen. Moles always gets the 1. And then with nitrogen is going to be its molar mass, which is 14. Okay, so let's go ahead and run the math out on that one as well. 31.08 divided by 14 gives me about 2.22 moles of nitrogen. Okay, at this step, when we're converting to moles, I think it's really important that we keep a few decimal places, okay? I would suggest at least 2. If we try to round this too early, it will end up throwing off our ratios for our next part. So keep some decimals when you convert to moles, okay? Don't try to round that to 2 right away, okay? Keep some decimals when we're converting to moles, okay? And then our last one, we're going to get rid of grams of oxygen and go to moles of oxygen. Moles gets the 1, and grams would get, for oxygen, 16. Okay, is this mole conversion coming back to us a little bit? Yeah. Okay, we're going to get rid of grams by using its molar mass. So 106.6 divided by 16 gives me 6.663 moles of oxygen. Okay, so I've done my step of converting each of them to moles. Now look at your process and see what's my next step supposed to be. What's my next step going to be?
Divide each element by the smallest number of molecules.
We're going to divide by the smallest number of moles. So which one of these gives me the smallest number of moles? Nitrogen. Okay, so I'm going to take that one divided by itself, which would mean I have 1 nitrogen atom. I'm going to take this one divided by 2.22 because this is our smallest number of moles right here. And when I do that, I'm going to get really, really close to what? Not 0, 1. I'm going to get really, really close to it because I'm almost dividing by itself. So I could run the math, but I know I'm going to have a ratio here that needs 1 hydrogen. Okay, then I'm going to come down and do the same thing. Divide by 2.22. Right? I think you can put it in your calculator, but you probably can guess what our ratio is going to come out to be. 3 oxygens. Okay? Yeah, because it's 3.001. So that's really close to a whole number. We're going to go ahead and round that. At this step right here, after we do the dividing, we're hoping they come out to nice whole number ratios because that's how we have to build formulas, in whole numbers. We can't have a half of an oxygen atom, right? We want this step to come out at whole numbers. So that's why we don't round in our previous step. But when we do this division right here, we're hoping they come out in nice round numbers. And so at this point, now I can just build my formula. I need 1 hydrogen, 1 nitrogen, and 3 oxygens. So my formula is HNO3. What's the name of that molecule? Tell me, first of all, is this molecule right here, is it ionic, covalent, or an acid? It's an acid. Good, because hydrogen comes first. And it's coming from nitrate. So we would call it nitric acid. Yep, it's coming from nitrate, so it would be nitric acid. Right, it's coming from nitrate, so it would be nitric acid. Very good. So now we have an alternate way to build a chemical formula, right, if we don't have their name. Okay, so for this next problem, we are given our value in percentages, so we need to make that switch right at the beginning. Okay, so we're going to say 89.14 grams of gold and 10.8 grams of oxygen, right? All we're doing is swapping that unit for grams, and we're acting like we're able to examine a 100-gram sample of that because they're going to add up to 100%. So that means they add up to 100 grams. So let's go ahead and convert here, right? I want to get rid of grams of gold and go to moles of gold. Moles gets the 1, and then molar mass for gold is 196.97. So I think we can round that to 197. Okay, so let's go ahead and do the math there. 89.14 divided by 197 gives me 0.452. All right, I don't want to round that. I want to keep some decimals in this step. Okay, so this is moles of gold. This is not the part of it that we should get nice, pretty round numbers. Okay, that's our next step. Okay, so we're going to do the same thing for oxygen. Convert from grams to moles of oxygen. Moles gets the 1, and oxygen weighs 16 grams. So 10.8 divided by 16 gives me 0.675 moles of oxygen. So next step would be to divide by my smallest number. So this one's my smallest, right? 0.452. So I'm going to take that divided by 0.452. I'm always going to take one of them divided by itself, right? Because one of them is the smallest one. So this means I need 1 gold. And I'll take this one divided by 0.452. And what do I get here? Right, I get 1.49, which is about 1.5. Can I round that to a whole number? No. Okay, so this is where, I put this example in on purpose. This is where we have to keep the ratio intact, but we need to get them to whole numbers. Okay, so here's what would happen. If I was going to build my molecule, it would look like this. AuO 1.5. Do we ever have molecules that look like that? No. So how do I keep the ratio the same but get them to whole numbers? No, I don't want to round it because I don't want, my ratio is not 1 gold to 2 oxygens. It's 1 to 1.5. What should I do?
Can you make it 3 oxygens and 2 gold?
Bingo, right? I'm going to multiply by some number to get them into a whole number. So it's going to be AU2O3. Very nice. Okay, so I'm gonna multiply that. So my ratio is still intact, 1 to 1.5, but they're both whole numbers. Okay, does that kind of make sense? we're going to be talking about something called empirical formulas. Okay, and empirical formulas, oh, sorry. Okay, I'm screen sharing to somewhere, but not here, I guess. Let's try this one again. Thank you. Okay, so we're going to talk about something called empirical formulas. And empirical formulas are basically the most reduced version of a formula. Okay, the most reduced version of a chemical formula is called its empirical formula. And so that means every ionic compound that we've built so far is an empirical formula because we always reduce those down, right? If we had aluminum phosphate and we had left it Al3PO4 3, that would be no good, right? Because we know we have to reduce those 3's down. Would we agree? So the correct formula, AlPO4, this would be the empirical formula, right? It is the most reduced version. Where empirical formulas become a little bit different is with a covalent compound. And we have a covalent compound maybe that looks like this, N2O4. And we would name that dinitrogen tetroxide, right? But with covalent compounds, we don't reduce them. Would we agree with that? We don't reduce them. And so what we're going to look at here is that N2O4 might be the formula of a particular compound, but its empirical formula is going to be the reduced version of that, which would be NO2, right? We're going to reduce that all the way down. Does that kind of make sense? So this would be that formula's empirical formula. And then this non-reduced version is actually called the molecular formula. And we're going to get to that a little bit more tomorrow. Okay, so in covalent compounds, you can examine both the reduced version and the non-reduced version. The difference is that those two compounds behave differently. They're not the same compound. They don't have the same characteristics or behaviors or anything like that. They just have the same ratio of elements. Okay? And so today we're going to deal with empirical formulas, which means we're going to build the formula to be the most reduced version that we can have. Okay? So the way we start with an empirical formula is we start with its percent composition. Okay? And so I'm going to give you kind of a list of steps that we're going to follow, and then we're going to put those into practice with an example. Okay? So for an empirical formula, we're going to start with percent composition. Okay? And so what that means is might say it's 30% nitrogen and 20% carbon or oxygen or whatever, et cetera, right? It's going to give us this starting amount. And so for us to be able to work with those percentages, we're going to just switch them. We're going to switch the percentage to grams. Okay, I'm not going to say convert because we're really not going to convert. We're just going to make a switch. We're going to convert our percentages to grams. And so what that does is it allows us to act like we're dealing with a 100-gram sample of this unknown compound. So if it had said we have 30% nitrogen, instead, we're just going to say we're dealing with 30 grams of nitrogen. That's it. We're just changing the unit on it to be able to give ourselves something to work with. Okay, so step one is we're going to change our percentages to grams. I'm not calling it a conversion because I don't have to do any work to do that. Okay. If our starting amounts were already given to us in grams, then great. I don't have to do any extra work, right? I'm just going to keep it in grams. Okay, so that's kind of step one. Step two is to convert each element from grams to moles. Okay, so I want to get them all into moles because that allows us to compare quantities in a way that makes sense, right? And we can compare apples to apples that way. So I'm going to convert all of them from grams to moles. And we know how to do that. It's just like a one-step simple conversion, right? Using molar mass. So that conversion is easy. Once we've done that, okay, this is going to make more sense when we see an example problem, but I want to have the steps listed out here first, okay? Once we've done that, we're going to divide each by the smallest number of moles. Okay, we're going to take each of those mole values and divide them by the smallest number of moles we have. So if one of them's 2.4 moles, one of them's 0.8 moles, one of them's 3 moles. We're going to take each of them divided by 0.8. And that's our smallest number of moles. This step right here gives us a ratio. A ratio of how those elements are going to fit together. So once we have that ratio, then our last step is just to build our formula. Okay, typically we can build our formula in the order our elements are given to us. Okay, they typically list them in that order. If they don't, we'll kind of build our formula from left to right on the periodic table. Okay, so but typically we can build them in the order given. Okay, I won't count you off if you build them in the order given and it happens to be incorrect. Okay, typically we can build them in the order that's given to us. Okay, so there's kind of our outline and our steps. I want you to go ahead and get out that set of example problems I gave you now, because we're going to jump to that and just go in with some examples here. So keep these steps out in front of you, and we're going to do the practice problems that are listed on these example pages. Okay, I printed them out for you just so you weren't having to write everything down for that practice problem. Okay, so let's go to the side that says